The reason I did that is because we're going to transition into another type of problem to finish up this part. We're going to connect the two things we know about a mole and the thing we know about a molar mass. Okay, so they look similar, but they're different. So we're going to work these two problems. A sample of lead contains 7.87 times 10 to the 23rd lead atoms. That's cool. And it says, what is the mass of this lead? Okay, so I'm going to show you, but actually you're going to use lead's molar mass, and you're also going to use Avogadro's number. You're going to use molar mass and Avogadro's number for the next one, too. It says a sample of lead has 0.330 grams. What are the total number of lead atoms in this sample? Okay, so I'll kind of show you how that works. But keep in mind, they both deal with lead. And anytime we have any element, we can say that we have, if we have 1 mole of atoms, we have 6.022 times 10 to the 23rd atoms. Okay? The other thing about lead, oh, sorry, I'll finish that thought. Okay, so if you have an equality like that, atoms to moles to atoms, you can go ahead and use that equality as a conversion factor to work your problem, and we definitely are. So the other thing about lead is on the periodic table, lead actually has a decimal number of 207.2, and that is the two things. We said that's how much a lead atom weighs in atomic mass units, but that's also for lead the grams you need to set aside to get 1 mole of lead atoms. Okay, so actually we can kind of unpack that too in several ways. So that is a physical property of lead. We could say there are 207 grams of lead per 1 mole of lead. We could say 1 mole of lead will weigh 207.2 grams of lead. We could flatten it out and we could say it's a physical property for lead. 207.2 grams of lead is equal to 1 mole of lead. So we're just kind of setting ourselves up for this problem to go ahead and use it to get from what? Grams to moles. And if you look at the previous slide, we can get from back and forth between atoms and moles with the previous slide with Avogadro's number. So that's definitely, we're going to have 2 conversion factors for these problems. So if we start with the first problem. The first problem basically, sometimes I don't even read the problem, I just see a number and I look at what the units for that number is. So I see 7.87 times 10 to the 23rd atoms. Okay? So I think of that, I might doodle it down. I said, what is the mass? What is this? What is the mass? Okay, so I might put grams clear over here on the right-hand side because that's what we're trying to get to, and I might put atoms on the left-hand side because that's what we have to use. Okay, so we're given atoms, so I'll put that on the left. Okay, now we know we can get from counted number of atoms to moles using Avogadro's number. And that's exactly how we're going to execute this problem. Execute sounds so evil. But we can get from the counted number of lead particles to moles of lead using 6.022 times 10 to the 23rd, recognizing 1 mole. And if you want to, when I'm working a problem like this, if I'm doodling underneath the problem statement, a lot of times I will leave out the word lead if it's all lead. Okay, so 1 mole is equal to 6.022 times 10 to the 23rd atoms. So once we have moles, we can go ahead and get to grams using the molar mass, which is kind of like one of the problems that you guys did this morning. Once you have moles, we can use the molar mass to get to grams. And we said for lead, the molar mass is 207.2, and that's it. Okay. So as we work this problem, again, the thing we're going to start with is the thing what I say is unique to the problem. And so that's your 7.87 times 10 to the 23rd atoms. I know this says PB or lead atoms, but you could just do atoms if you wanted to because it's under the problem statement. I would put that over 1. So now we're going to go from atoms to moles. We're going to use that equivalency statement, that first blue equivalency statement. We want to put atoms in the bottom and be left with moles. So it will look like this. We have 1 mole over 6.022 times 10 to the 23rd atoms. So now atoms cancel. We're left with moles in the top. One last thing is we need to take that moles to grams. And to do that, we're going to use the molar mass of lead. We're going to put moles in the bottom and grams on the top. So the third term looks like this. So the third term is down there in the bottom. 207.2 grams over 1 mole. So now unit-wise, we're great. We have units of grams, which is what our target was. So we need to round this. It looks like we need to round according to 3 significant figures. So the mass of lead then is 271 grams. Okay, any questions about that? Okay. So the next one's kind of similar. It is, but it isn't. It's basically backwards. The next one, we have mass and we want to get to number of atoms. So in this one, we're going to start with our grams. We're going to go from grams to moles using the molar mass, which is 207.2 grams is equal to 1 mole. And then we're going to go from moles to counted number of lead particles using Avogadro's number. 1 mole is equal to 6.022 times 10 to the 23rd atoms. So to execute this, the first term is going to be the thing unique to the problem, which is 0.330 grams of lead. I would usually put that over 1. Now if I want grams to cancel, I'm going to use what I call the flipped version of molar mass. So the second term would be 1 mole over 207.2 grams. Grams will cancel, I'm left with moles. Then if I want to get from moles to counted number of atoms, if I want moles to cancel, I can make a third term be my 6.022 times 10 to the 23rd atoms over 1 mole. So moles will cancel, I'll be left with atoms, and that's it. So it looks like we need to round according to 3 significant figures in the first term, 4 significant figures in the molar mass, and there is uncertainty in Avogadro's number. So 4 significant figures in Avogadro's number. Round to 3 significant figures, I got 9.59 times 10 to the 20th atoms. If you're working these problems, it's probably good to think that you're, let's see, how do I say this? If you're going for the number of atoms, it's probably going to be a big number like this, okay? If you're going for moles, it's usually kind of a small number, kind of between 1 and 0.0001, something like that for moles. I don't know, just usually it seems like. That's a big number. That means if you have a fraction of a gram, like a third of a gram of lead, then you have, you know, on the order of 10 to the 20th lead atoms. Makes sense. Okay, so we'll take a look at these right quick. These will be due on Wednesday, because this class doesn't meet on Monday. And so it looks like this. And I'll push these hints out there just because I can, and it's easy. Let's see. If it was hard, I probably wouldn't do it. All right. So the first one, the first two kind of go together. 29 and 30 kind of go together. Basically, it's just a grams to mole question. So in purple, I have how you're going to do that. For those elements, you're going to have to use a periodic table, look up the molar mass for those elements. Okay, and I went ahead and did C for you. So for TA, and I had to look, it reminds me of the spider, tarantula, yeah, so it's tantalum or something like that, because I wouldn't know. But its molar mass is 180.95 grams per mole. So if we use the flipped version, then grams will cancel, we'll be left with moles. The next one is for 30, it's what we call a moles to grams problem. And we're going to use, again, a periodic table and the molar mass for these elements. I went ahead and knocked it out for xenon. Your first term is, in this case, always going to be the moles that you want to get to grams. So for xenon to be the 68.1 moles over 1, and then use the non-flipped version of the molar mass of xenon to have moles cancel, be left with grams. Works pretty good. And then the other two kind of go together, and they look like this. Just a single question, but actually it's kind of similar to what we just finished up with. If you read the 35, the element is aluminum, you're going to need to know that because you're going to use the periodic table to find aluminum's molar mass. but you're going from grams to number of atoms. So you go from grams to moles using the molar mass, and then from moles to atoms using Avogadro's number. And then the next one, switching it up, looking at platinum, you're going from counted number of atoms to grams. So you'll need to look up what platinum's molar mass is, and then you're going to use that at the end. So you're going to go from atoms to moles using Avogadro's number, and then you're going to go from moles to grams using the molar mass of the element. So, yeah, not bad. Okay. So let's go on and do a few slides. I kind of know where I want to stop already. I put a blank slide there. Okay. So some of this is going to kind of look like review. So we kind of talked about the overall structure of an atom. We talked about how do you get the mass of an atom. We talked about the concept of a mole, and actually we're going to definitely carry the concept of a mole through the course, kind of applying that to compounds here later on. But now I want to kind of go back, draw back to one subatomic particle in an atom, the electron. Okay, so the electron is a big hairy deal. The electron, we said, in fact, I was talking to a colleague the other day who teaches something else that's not even science, and she's like, atoms are just underestimated. I'm like, yes, they are. Thank you very much. So electron is the outermost particle of an atom. Electrons, actually, when we talk about compounds, are the things that connect atoms together. It's all about the electrons that make compounds that we know and love. But electrons can kind of come and go. We're going to see, actually, later on how an atom will give up electrons or take in electrons, depending upon how many electrons it has. So electrons are very important. Electrons have to do with chemical reactivity. So this actually is a slide that you probably don't have, but it's like what we know about an atom over time. I just think that is so cool. We used to think that atoms were just little blobs, which they kind of are. And then we started to understand the subatomic particles associated with an atom. So clear down here, and actually you're going to see mention in the lecture notes about the Bohr model, okay, and the Schrodinger model. So they're significant. The Bohr atom is cooler than the Rutherford model. The Rutherford model understood that there were electrons. But the Bohr model said, well, there's not only just electrons, but those electrons actually, can you see where those little orbs, there's some orbs that are closer to the nucleus and some orbs that are further away. So Bohr understood that actually there are electrons that physically reside closer to the nucleus, and they will have different energy than those electrons that are farther out. And then Schrodinger took it a step further and kind of piggybacked, understood that electrons actually have specific locations, but he did calculus and then understands kind of the region of space about the nucleus where an electron can be found. Okay, so that's the Schrodinger model. So just to kind of remind you how that works. So the Bohr model and the Schrodinger model both have electrons. Not all electrons are created equally. So we're going to see, and we're going to hit this next week, that electrons, for instance, around a carbon atom, we pick on carbon. Carbon, remember, is atomic number 6, so it has 6 protons in its center. If it's neutral, a carbon atom has 6 electrons. Those 6 electrons are not just willy-nilly. They're very organized. And we're going to talk next week how those 6 electrons actually have a very unique set of what we call quantum numbers. Okay, so here we're kind of seeing kind of the Bohr model where these are principal energy levels, and we'll talk more about this next week. But we have principal energy level. The variable for the principal energy level, the main energy level, is n. So we have principal energy level n is equal 1, 2, 3, 4, 5. So you recognize a few things. One is those energy levels, as they get higher, are getting farther from the nucleus. We're going to see actually that this is high energy, and this actually is low energy. Okay. And this thing is the nucleus. This is home to the protons and the neutrons. Now, I wish, because I teach astronomy too in the fall, I wish that they didn't use the word necessarily orbits, because that's what actually we use for what the planets do around a star. Okay, so the planets, the Earth orbits the sun because of gravity, okay, which is like a attraction between the masses of the sun and the Earth. Okay, it's not a gravitational thing, and electrons don't orbit the nucleus like that. Instead, actually, and I think I mentioned this before, they're in a cloud, and so they're kind of like, and they can't really, well, maybe they can kind of pop from here to here. They can do some cool things, but they don't, and they stay in place. We talked about this because electrons are pulled to the positively charged nucleus. Electrons are negatively charged. The nucleus is positively charged with the proton. So that's why they stay in there. But you're kind of getting the idea here. So as I said, the Schrodinger model is the most sophisticated that we have of an atom at this time. And it describes the electron as being in a cloud. And we're going to see that that electrons are unique, like the six electrons of a carbon atom are unique, and they actually all each one has their own little home. And it's funny because they don't share. You cannot share the same address as an electron around the same atom. You cannot. Okay. So when we talk about orbitals, that's the region of space that Schrodinger would say that you're most likely to find an electron, that particular electron. Okay. And I could animate this, but I don't have the file. It simply would kind of, it's what I've been saying. It tries to dispel the idea that an electron basically orbits the nucleus like planets orbit the sun. Okay. Actually, it's more of a cloud function. Okay. So one of the other things I want to talk today, just briefly about, is the idea, just keep on that idea of electrons can have low energy. Remember a minute ago I said n is equal to 1, that's a low energy electron. Or electrons can have higher energy. Then we talked about the principal energy levels, like n is equal to 1, 2, 3, 4, 5. Those are the principal energy levels. Actually, next week, we're going to kind of break those principal energy level down into they fan out into like kind of other little levels, okay? But the energy of an electron is what we say quantized. And a good way to kind of describe quantized is coming up. But quantized means that it can be here, okay, at this location with this energy, or it can be here at this location with this energy, I should say with this energy. It can have this energy or it can have this energy, but it can't have anything in between. Okay, if you've studied light much, the concept of the different colors of light is actually kind of packetized into little, what we call photons, and they have a certain discrete amount of energy. And that's kind of a similar thing that we have with the electrons. Okay, electrons can have this energy, they can have this energy, but they can't have anything in between. Oh, you guys have to write it down a lot for that slide. Hand cramp. Every once in a while you get one of those. While I'm thinking about it, I will mention that your next unit exam, I can't remember, did your last unit exam have like the first page had like definitions? Okay, maybe it didn't. A lot of time, my second unit exam, a lot of times it'll have like a set of like definitions, and this is one of the things I like to define. I mean, it may or may not. My unit exams, I switch them up, but so be prepared to kind of. I give you a definition, you give me what I'm trying to describe, okay? All right, so quantized values, they can actually, if we talk about kind of how high, like the elevation of somebody as being the thing in question, can you see where a chemist here, okay, those are really high steps that go up to his hip. But assuming that he can climb those steps, his elevation would be like discrete. Okay, discrete locations. So that elevation is quantized. This is more like a continuum, kind of. The dude could be anywhere on there. That's a pretty steep grade for a... Oh my goodness. Glad it's Friday. Okay. So we have a lot of things that are kind of continuous, okay? But the energy associated with electrons is not. It's got to be here, there, or there. So you can kind of think of it as basically climbing rungs of a ladder, where, and actually this works to a certain extent. The little picture we saw a minute ago, I could put the nucleus down here, okay, the nucleus of the atom here, and actually I could put electrons at these principal energy levels, and they are getting farther away from the nucleus, and they are increasing in energy. Now I'm going to kind of have to scramble that up a little bit, probably next Friday when we get to it, that it's not quite that simple. You can't just say, oh, the principal energy of this level of this electron is going up, so it must have higher energy, because there's a little bit of scrambling that kind of goes on there. But that's kind of generally the idea. Okay. I think this is kind of what I've been talking about. I guess I'll mention, this mentions the element hydrogen. Of course, hydrogen's unique because it's the simplest element. It's atomic number 1, so it has 1 proton in its nucleus. Most isotopic forms of hydrogen have no neutrons. So remember, actually, the mass number, which is protons plus neutrons, is also 1, which is kind of weird. All right, so one other thing I want to talk about is this idea. We've been talking about energy, okay? They're actually related to energy. There is something we call the ground state, okay? And I mentioned carbon. Carbon has 6 protons and 6 electrons if the carbon atom is neutral. If the carbon atom is in its ground state, all of those electrons are actually at their lowest possible energy level. But keep in mind that they all can't be at the same energy level, because the 6 electrons have to be unique. I just think that is so cool. It's an awesome system, you know. All right, so, oh, sorry. I guess there was more on that. So, and nature is like this a lot. If possible, it will fall back down to its lowest, its most stable form, its lowest allowed energy. And when we get going here next week, when we start what I say finding homes for electrons, it will be as those set of electrons are residing in their ground state. So compared to, or kind of the opposite of ground state is excited state. A really good example, common example that's mentioned here with excited state is when we, on 4th of July, observe those awesome fireworks. And it happens a lot, but a lot of other times too. But basically what they're doing is taking particular elements that give a particular color, because you've seen those different colors. Different elements will give you different colors. So basically what they do is they time their firework to when it is where they want it to go ahead and give off the color. Basically they go ahead and take that element and they excite the electrons around the atoms. Okay? And then basically those electrons will go from excited state back. So it took some energy. Did you see that? It took some energy. It takes energy to do that. Okay? But as the electrons go from their excited state back down to their ground state, then they emit this discrete energy, this discrete color. And that's the fireworks thing going on. So, all right. So, electron orbital. I always kind of think of Schrodinger's model there. Basically, electron orbital is a region of space you're most likely to find an electron. That general region of space then will have a particular energy associated with it. We're going to see actually electrons that are in a particular orbital will have a particular spin as well. But so. And not all orbitals even have the same shape, because like we usually think of the nucleus as being round. I guess it's probably round instead of lumpy. I don't know, we have protons and neutrons. They could be lumpy. And then we usually kind of think as the electron cloud as being kind of what we say spherical, but it's not always even spherical shape. That is so cool. I just think that is so cool. Okay. So my blank slide says that's where I wanted to stop, because actually the next few slides, if I go over them, We'll just have to do them again on Wednesday. I'm taking personal day. Okay, so that's all I have. Just that one homework due for Wednesday.